Yeah, I think we can get started here. So good afternoon, everyone. So today we are going to have this webinar, and the topic for today is webinar on coding guidelines for DO254 for DAL A2E certification. And the webinar is going to be for 1 hour. So it's 3:30 in India right now. So it will be 3:30 to 4:30. So first 45 to 50 minutes is going to be the presentation, and then last 15 to 15 minutes we are going to have for the Q&A. So so if anybody has a question, what they can do is, since it's a webinar, you can go to the Q&A tab. So in the right bottom half, you can see there's a tab for Q&A. So just go and press the Q&A tab and you can ask your question. That is one thing. And we will try to take all the questions towards the end as much as possible. And yeah, I think, yeah, and the session is also going to be recorded. So in case you're having internet connection issues, or in case you're joining in late, at the end of the webinar, what we're going to do is we're going to send the recorded session to all of you. Right. So in case there's some internet connection issues or power issues for some reason you don't have to worry. The session is completely recorded, right? So let me run through the introductions here. So in the panelists, we have a couple of people. First person I have is Godfrey. Godfrey is the founder and CEO of Prodigy Technovations. He has around 25 years of experience in test and measurement, and he's worked in HP Agilent before starting Prodigy Technovations. So Godfrey, you want to say hello or give a brief?
Yeah, thank you everyone joining this session. Really appreciate taking time out and attending this session. Yeah, I think we are here to support Aldec products, and we have a team in India. Nitin, Khalil, and Raghavendra who are our Aldec product support team. So I think that's about I like to introduce. Yeah.
Okay, thank you, Godfrey. And so we have one of the experts here, Alexander. So I'll just read his brief introduction when I get. So Alex, he has around 25 years of experience. He's worked on FPGA as well as ASIC design and verification. Previously, he worked with IBM, Nortel, Ericsson, and Synopsys. I mean, all the big companies he's worked across. And most of his designs have been, multi-million gate designs. And he's one of the experts in LINT, formal property checking, dynamic simulation, and hardware-based assisted acceleration, right? And he's got his master's in electronics and electronics from Israel Institute of Technology. So welcome, Alexander. Alex, yeah, I'm handing over the session to you. You can get started from here. And I'll join in around 45 minutes from now if people have any questions. Thank you.
Hello, everyone, and welcome to our today webinar. And the topic of webinar is coding guidelines for the DO254 for DAL A2E certification. Let's start from agenda of webinar. First of all, we'll talk about HDL coding standards for DO254 compliance. Then we will go through review of what we have, and I present DO254 plugin, rule set plugin review. During this review, we will go through some examples. I will show you a small example of FSM verification. Then I will talk about other important topics for the companies who have multiple multi-clock chip PGA designs. And we're talking about clock domain crossings. And there I will show you another example, which is much more bigger example. It is real IP core from open cores, Minimac IP. And we will go through Minimac IP verification with the DO254 and then CDC rule set. We will talk about tool qualification for DO254 and as already been said, summary and finally Q&A. Let's start talking about HDL coding standards for DO254 compliance. So I'm not an expert on the OT54 by myself. There is other people who are experts, and I can refer to them. But in short, FAA ordered 18110-105A released in 2017 calls out the need for HDL coding standards consistent with system safety objectives. And the latest AMC 2152A released in 2020 calls out the need of HDL coding standards, not only for DALs A and B, but also for DAL C, which is actually increases the importance of using also design verification tools such as Alint Pro for design verification for the OT54 compliance. Basically, HDL designs with design assurance levels DAL A and B and also C must now establish conformance to HDL coding standards. There is no official list of the OT54 HDL coding standards. That's important to understand. There is no document describing those rules one by one. Some guidelines and list of rules proposed by the OT54 user groups in 2010, and our plugin also contains these proposals as well. Once a company has to go through the compliance, so the company has to prepare coding standard and is a part of planning process under 254. These coding standards must be reviewed and well documented, must be realistic. Organization must follow the standard and must be consistent and so on. And then basically once a coding standard is developed, the company has to enforce the standard for the company, which is really important. It's important to enforce the standard. And here, Alint Pro actually really helps provide great help for the company to enforce the company standards. And also we propose our own standard company may follow with the OT54 rule set. This rule set includes 88 HDV/HDL coding standards, 100 Verilog coding standards, and 58 CDC coding standards. A few words about automated review with Alint Pro. Basically, we're talking about design rule checkers for RTL verification, checking coding styles, naming conventions, RTL and post-synthesis mismatches. The way basically Alint Pro works by itself, it's a kind of a light implementation tool. It runs through compilation, it parse, elaborate, synthesis, and then we also load design constraints on the very early design stage together with RTL, and we can verify compliance of design constraints on RTL. We can verify clock domain crossings and many issues. Basically, what we do, we parse, elaborate, implement netlist. We implement netlist on technology-independent library, not on, for example, like vendor libraries, but technology independent one. And then we do different checks on different levels. We do have checks on parse stage. We do have check on elaborate stage. We do have check on netlist after synthesis. We do have check once we load design constraints, and we check also with design constraints and so on. So we check RTL on very different implementation levels. We provide customized reports. We are able to import designs as is from other ALDEC tools such as Active HDL Riviera Pro, but also we are able to import design tools also from design vendors such as FPGA vendors such as Xilinx and Intel FPGA. So we can just, with one click, you can import your Quartus projects, your Vivado projects, your IC projects into the Alint Pro environment. And we also support all libraries, so you don't have to worry about libraries working with FPGAs. All of them are pre-compiled, and you can use them also for linting and also for CDC verification. Let's start talking about the OT54 rule set categories. So basically, the actual plugin contains 3 categories. The same are described usually in, in the documents, and secure code practices. The first one ensures that a coding style supporting safety critical and good digital design practices are used. Second is design reviews, intended to automate design reviews and make code comprehension easier. And finally, safe synthesis ensures that a proper netlist is created by synthesis tool. Let's talk about contents of the secure code practices. It contains checks for assignments, clocks and resets, declarations, instances, racing conditions, which is important. Also, as mismatching bit widths, another very important part, which may be missed, especially in Verilog and System Verilog, sensitivity lists, subprograms, and finally, checks for synchronous FSM. Let's talk more deep on show examples about assignments checks. Here we're talking about duplicated assignments, and the upper example is about it. Let's say we have two duplicate assignments, assigning the same signals multiple times in the process. Mixing of blocking and non-blocking assignments, which may cause race conditions and some and the simulation to synthesis mismatches. It's really important to eliminate them. Proper implementation of three-state drivers and buses. And non-blocking assignments in sequential process. Other part is secure code practices, clocks and resets. We are checking clock gating. So basically, the good idea is to avoid clock gating checks. But if it exists, it requires proper isolation. Using on top level only also. Internally generated clocks and reset checks. Whenever you have internally generated clocks and resets, we also provide checks. We find those instances which generate internally clocks and resets. We extract clocks and reset tree out from design. We present them on our clock and reset viewer, and I will show you how we do that. We analyze them and we do all this kind of checks. We check also clock and reset in inferences for proper reset polarity. You can define which polarity is, for example, all flops in your design, all sequential elements of your design should follow, for example, negative H polarity, and so on. You can also define whether you want to work with a proper reset type for all your sequential elements should follow, for example, it will be only synchronous or only asynchronous, or you can actually you may combine also synchronous and none, for example. Let's say some flops from data pass are not non-reset flops, and others in control logic, let's say, has to be only synchronous reset. So you can define this combination of reset types, and then every sequential component will be checked for proper reset types in your design. Secure code practices, declarations. So once we work with VHDL, it's really important to check correct usage of VHDL data types, using proper packages, avoid unsafe data types, such as bit, for example, specify ranges for integer data type, proper range declarations, always descending range down to 0, use simple signals for array indexing. This is, for example, here we have a complex signal inside as a memory index, and we actually warn about that, asking designers to actually bring this complex signal into the variable, and only then use this variable as an index. Hard-coded declaration usage. All declared object signals has to be used. No redundancy and no, for example, like no dead code. Hard-coded values. Avoid hard-coded numbers and reset assignments. Here, for example, we have some hard-coded values, and for clarity and also for reuse, it is much it is better to actually to avoid those hard-coded numbers, but then define them, for example, as generic or as parameter in Verilog, and then use them in the code. Let's talk about instances. So once we instantiate our components, or there is a need to avoid ordered port connections, match port and connected signal names. This is another requirement from some companies, and we also check this, that signal connected to, for example, to instance has the same name as the instance port. Avoid unconnected instance ports. For example, in this example, in this case, D3 port is for some reason unconnected, and we definitely flag about it. And as I say, we flag it on very early design stage. It runs basically. You have to use a lint pro as soon as you write your RTL code. And as soon as you do it, more bugs you find, and then it's better, which is much more, you will get much more safer code for implementation and also for verification. And then you will save time on, for example, verification finding bugs, and also on implementation, running unneeded implementation cycles. Avoid implicit net declarations. Here, for example, you see that implicit net declarations n I1, so there is no declaration of this net, and Verilog allows it, but it is really unsafe practice in Verilog language. Let's talk about mismatching bit widths. Match right-hand side and left-hand side bit widths in assignment. Right? Avoid mismatching in assignment ranges. Okay, like in this example, here we have a mismatch in assignment range because basically here we put mult in general, and mult here will be treated as 16-bit variable, and we will immediately find this. ALINT-PRO will immediately find this error, and will actually require that O, which is defined as 4-bit, has to match, but will be assigned to the same bit width variable. Match bit width of each case item against selection expression. Okay, and match bit width of functional return values, and so on. Let's talk about sensitivity list. Sensitivity lists are really important, and also the issues with sensitivity list will actually cause simulation to implementation mismatch. Okay, so there is a need to define all necessary signals in sensitivity lists. Like here, for example, X1 and X2 were not defined in sensitivity list. Okay. There is no need to define unnecessary signals in sensitivity list. Also, there is no need to define constants in sensitivity list. Okay, it's just redundant code. Do not define signals in sensitivity list that are assigned within the same process. Okay, and do not use the signal which is the same the same process as statement it was assigned. For example, in this specific case, we assign to error code, and then we actually use this as error code value in the same process. Okay, so we have to avoid such definitions. Subprograms, we also check for subprograms. Do not read and assign global signals in a function body, only local signals. We don't want to do to actually call for other signals out of subprograms, let's say function body, to do calculations. And actually, this will actually make functions really portable and reused within different designs. Function return value should be defined in all the possible cases. Okay, and a function should return at the end of its body only, and function should not return in conditional branches. Here, for example, we see that function returns in one of conditional branches, if else, and then returns again, which is a bad practice. We require return only once at the end of function. FSM checks, and now we are going to show. I'll go to show you an example. First example. So what ALINT-PRO does, in addition to run design checks, ALINT-PRO helps you to explore your design. And I will show you right now how to start with ALINT-PRO. This is ALINT-PRO GUI. Once you open it at the very first time, it will be empty. You don't have any workspace projects, nothing. Okay. So once you don't load your workspaces and projects, you will see on the right side you will see demo projects, and this is a great tool and great kind of help to start with ALINT-PRO and to understand how it's working and to play with it and so on. Let's open one of these projects, which is FSM VHDL. And FSM-VHDL is a complex VHDL, right? A complex FSM, and let's run linting. You can run linting from the flow manager And here you will see, I was talking about LintPro as an implementation, a kind of slight implementation tool. Basically, we go through parse, elaborate, synthesize. We definitely ensure that code is synthesizable on the very early stages of your design. Actually, it's very important to make sure that your code is synthesizable before you start to spending hours with Vivado, for example. And constraint in linting. So you can go through all this one by one through the flow manager, or you just can click this button, and then basically you run through all the phases. As you can see right now, we are going to tools running through the phases, and it's already done. Now, once it's already done, what you can do? First of all, you can see your design, for example, in let me see. You can see your design in RTL schematics, and we provide you schematics, and you can easily understand your you can go through design. You can see how it looks like. You can see a full design, or for example, you can go through specific component, specific, let's say, net or signal, and say filter in RTL schematic, and it will show you only this part of schematic you're interested in. And then you can explore it, go back and forth, and see how your design part of interest of design looks like. And then we have basically violations. Here in this design, we have to set up properties, project properties. And here in project properties, we have policy. In this policy, actually, I have many plugins, but now we're talking about the Auto54 plugin, and we're talking about this specific plugin. Those are rules. You can check and uncheck rules that are important for you. You can also configure some rules. For example, you can go and see, for example, do not overload a wire with too many drivers. And then you have also master state count parameters. So basically, many rules are parameterizable, parametric, and you can check these parameters for your design. Also, what you can do, you can change severity of a rule. If you change the severity, for example, from warning to critical warning or error, then you cannot pass the rule, basically the phase of, let's say, if this rule belongs to elaboration phase or the parse phase, so this phase will fail. You will see it as red, and you cannot actually achieve. You cannot lint your design basically, and this is actually very good for linting when you, for example, for kind of regression linting. When you extract a bunch of files, you define important rules, you run through those rules, and you want to get binary answer, linting passes or linting failing. Okay, so you can set our tool. You can also work with from only console mode, like batch mode. You can run linting in batch mode, and then you can do it for your designs very quickly and efficiently without avoiding review of designs. Now let's go through this specific example. It is FSM. We're talking about FSM, and now our design has different viewers, and we have netlist viewers, clock and reset viewer, RTL schematics. I already showed it. Control schematics. Let's go to FSM window for specific example. We'll see FSM example, and here we have FSM extracted out from design. It contains input signals, internal signals, output signals, and so on. We can go through issues, and here we have our violations grouped by DO54 chapters. You can group them actually different ways. You can do it flat, you can do it by files and so on, but by units. But now let's take a look on just group it by chapters, and then see synchronous FSM, safe FSM transitions. And here we have two issues. First one is avoid unreachable states in FSM descriptions, and second is avoid deadlock states in FSM descriptions. So what you can do, you can just click on you can click on the issue actual violation instance. Actually, first of all, what you can do before doing that, you want to understand better the rule, basic documentation of the rule. What you can do, you can click you can actually double click on the rule itself before going to actually rule violations. Once you double click on the rule, you will see on the right side window, rule description, your documentation of this rule. And here you can read about documentation, about what is good, what is bad, how rule is doing this, it checks. And also there are examples showing this rule violation. And it's very important, in my opinion, if you don't fully understand the rule, to try and play with this rule with example. And examples are both for Verilog and VHDL, right? In the specific, it depends on the rule, but this rule is VHDL, so we have only VHDL example. But and examples are also for good case and bad case. So you have issues with design and then violations. You find these violations, and then you fix your code. This is another good example. So these examples are really important. Once you go through the tools, you want to understand better how tools are working. Okay, so and then we go, after we read documentation, we go through actual instances of these violations, and then you can look into the source. Is one option. Definitely it jumps to the source, but more interesting, you can show in a FSM graph. And here what we do, we also extract a FSM graph, and this FSM graph can be also viewed from FSM viewer. Let's say show in graph, you will show the same picture. We extract the FSM type, which is more mealy or mixed, and we extract definitely other FSM parameters such as encoding type and so on. Amount of processes, let's say it has to be only 2 and 3 processes described in RTL for the FSM, not only one, like mixed process and so on. In this case, we have basically a stand state is unreachable. And why it is unreachable? Basically, because we have this red cross on this arc. And why we have this cross on this arc? We can go to the source and see that that here we have this count, and we have condition if count more than 7, then we want to go to this state. However, count by itself is defined as only 3-bit is in the range 0 to 7. So it cannot be more than 7. And that's why we analyze the code. We also have small kind of BDD engine, like small formal engine, which extracts conditions that cannot execute, and the branches that cannot execute. And then we actually mark this this transition with red cross. And because of that, this group of this states S10 and also S11 and S12 are becomes unreachable. And second one is avoid deadlock states in FSM description. So deadlock state is state without exit. And here we have S13, this kind of state that there is also arc into the state, but there is no arc out of it. Okay, and this is about FSM verifications. A very quick example, and I will show you later another example. I was talking about Minimac example, and we will go through different checks and also CDC checks with that example. Okay, so one of important checks also I have to mention here is, especially for design safety, is in a case of state corruption, transit to defined FSM state. It's really important because in the field, for example, what happens if your state is corrupted? And if your state is corrupted, so usually it is really important to go from this corrupted state, and this corrupted state value can be undefined. It can be, for example, it can go out beyond, for example, it can be, for example, 3 in this case, in this example, and 3 is not defined here. What happens if you get by chance, for example, bit corruption of FSM state as a 2-bit 1-1? So in this case, if we don't specify in default nothing, we won't be able to exit out from corrupted state. So it's really important to make sure that every corrupted state, FSM can exit from any corrupted state, and therefore we have default case. And in default case here, we specify that next state default is for all the rest of values and also undefined values. So next state has to basically go to reset state. I already mentioned the demo. Let's go forward. And here we're talking about coding styles declarations. Here we're talking about port description order should follow a pattern. For example, you can define in your company that first of all, you want to specify clocks and then resets, and then input ports, and then output ports, or in any other order. And once you specify any interface of any entity or module in Verilog, right? Also, we're talking about comments. It has to be well properly commented. Add comments to object declarations. Describe one object per declaration. Declare one object per line, and so on, to make code clear and concise, and also much more reusable. Coding style statements. Do not describe multiple statements declarations in one line. Use statement labels, including ending labels. Do not use same names for different objects. It's really important. Just sometimes languages allow doing that. Indent each level of the source code. And we also check indentation, and and also using states instead of tabs, because tabs may shift your code in different editors. Coding style, commands, and files. We ensure consistent file header, and we also provide template of this header. This template is, you can change this template, and you can feed this template to your company guidelines. Ensure sufficient comment density. Ensure commenting of design constructs. You may define that you want to comment for any design, for any signal declaration, for any process, and so on. And if you don't, this comments in this specific case, there are some violations, because process is uncommented, enable assignment is uncommented, and so on. So you can actually tune this rule. You can these rules. You can configure them to your company needs. Let's talk about other part of the AUTO54 rule set is safe synthesis. And as I already mentioned, that ALINT-Pro is kind of light synthesis tool as well. It checks synthesizability of the code on the very early design development stages. We check for assignments, conditional statement, implied logic, race conditions, register inference, sensitivity lists. For safe synthesis assignments, we check that do not use multiple waveform and optional delay expressions in assignments. Do not use records in VHDL. Do not use register initialization assignments. Okay, like avoid undriven signals. Avoid long combinational passes. So in addition to checks on sensitivity, we also provide fast checks on efficiency of your design for implementation. For example, we check long combinational passes in the very early stage. This check is not precise, because you can get this information precise only after implementation, but it is kind of rough but very important checks to show you how many logic elements are in your combinational passes after this fast synthesis. You can extract those passes, and also what is also important is how many these passes are in your design. If, for example, you have many long passes, and each path, for example, is at least, let's say, 20 gates, or let's say, you can define also limits during this check. So your RTL code maybe is not efficient for timing implementation, and you have to do better job in optimizing your code. And as I said, we do it in very, very early stages of design development. Here, for example, we have violation because of this complex combinational logic path. Paths with depths up to 6 are detected to the spin, and this 6 or 7 or 10 is your choice. You can define any number based on your design experience. Safe synthesis conditional assignments. Do not describe case statements with overlapping items. Here, by mistake, we see that this case is defined twice for bit 001, and this is basically our overlapping one. Case statement should always have others default choice. Do not use case X and case Z statements, because they do, in some cases, you can get a simulation to see this mismatch with using this case X and case Z statements. And since Verilog, it's better to use case inside instead of both of them. Do not describe unreachable conditions. Okay, and for example, here is unreachable condition in always com loop. First of all, we have if A, and then else if A and B. However, if A is 1, you always go to the first condition, and the second condition also requires A being 1, but because it's in the first branch, so you will never reach second one. And we easily extract all these situations, and they may be much more complex than my example. And sometimes it's very difficult to see it from design. Use single bit signals in conditional expressions. Do not use with select statements. Safe synthesis implied logic and rate conditions. Do not connect in and out port directly to input output ports. Avoid delayed chains in digital logic. This is an example of delayed chain, and at the same time, it's an example of a combinational feedback. Basically, it's oscillator implemented in design. So we get 2 of those warnings here. Avoid feed-throughs in digital logic. If you have blocks, you have signals, which is you have combinational passes from your block inputs to your block outputs. It's allowable, but it's a bad thing from timing perspective, because then you can connect your output to some other passes, and then in total, basically your combinational, your timing pass increases. It's really important to break your timing passes, to break each one of your timing passes within the module, right? It's kind of timing safety also. It's really important to optimize design for timing in a very early stage of design development. Register inference. Do not describe multiple independent conditions in the process. Here, for example, here we have in one process we have if, and then we have case. It's really a bad practice to do that. Avoid latches. Definitely we find latches. We report about latches and make sure that there is no latches. Your code is does contain latches for implementation. Each register should be controllable from its input. So basically there is no fixed values going to, for example, to register data pin. Avoid using variables to infer sequential logic. Here, for example, we have variable, but this variable then is actually assigned to itself with not. By itself, this variable creates a register, flip-flop in design, which is a bad thing, and we provide check on this specific situation. Sensitivity lists. Do not use different clock edges within the same process. Here, for example, for some reason we used POSH1 clock, and which is a really bad coding style. Do not use different edges for clocks with the same event control statements, and some other weird kind of coding styles. Maybe some people may try to use, but we definitely warn about all of them. Okay, so let's talk about. This is a slide about recent DO254 plugin enhancements, and the last year we did lots of work on DO254 plugin improvement and enhancement, and to ensure that we will get fail-safe design. We get lots of feedback from customer experience for companies working with DO254, and basically DO254 we enhanced it with 62 insertional rules in different for all the 3 chapters. Okay, so we went through the DO254 plugin review right now, and now we'll go to CDC verification with Alint Pro. If you have multi-clock designs, so your design require CDC clock domain crossing verification, which is separate topic to the DO254 plugin, but you have to verify your design. Otherwise, you will have functional issues. You may have functional issues, and your implementation will be glitchy at least, and and actually will not be fully synchronous in terms of like you want to achieve complete determinism in your design, but because of CDC issues you may not achieve it. Alint Pro provides Aldex CDC plugin for in-depth CDC issues analysis, 58 rules for clock, reset, CDC, and RDC verification. RDC is a reset domain crossing. So with this clock domain crossing, but if you have number of resets, I'm talking about asynchronous like resets. So in this case, we also want to check domain crossing between different resets. CDC flow to reduce complexity of CDC verification. And what we do here with these flow managers, and I already showed you the tool, we break the complex tasks by parts. First of all, if you want to run CDC, first of all, you want to run your clock verification and make sure you don't have any clock issues. If you have any clock issues in your clock trees, it will be much more difficult to go to CDC stage. So first of all, you have to clean up your design from design entry perspective. The important rules has to pass. Then you want to make sure that your clock trees are clean, and you want to see these trees. Then you want to set up your design constraint files and your phases. And we require actually a designer to have a SDC file or XDC file, basically design constraint file added to your design for CDC purposes, because this file contains phase information, both on clocks, on whether you have these groups of synchronous, asynchronous clocks, and so on, and also which clock phase belongs to each input and output of your design. Finally, we also do reset, not finally, but we also do reset verification. And once we do all the stages, then we can go to actual CDC verification with already stable design, with already and then we actually find only CDC related issues. And once we do a topological analysis, we extract the clock domain boundaries. We extract design structures. On those domain boundaries, we extract all the synchronizers and make sure they are valid. At the end, once we run through structural verification of our design, we also extract CDC assertions for dynamic verification, because structural verification is not enough for CDC, and you also have to run assertion extraction and also use assertions in your test benches. Clock domain cross verification flow. I will quickly go through the slides because we don't have enough time here, and I would prefer better to show you actual design example. So let's first of all talk about, as I said, we have a separate ALDEC CDC rule set with 58 rules, and we check for different things in CDC rule set. We also check not only CDC issues, but also clock reset tree issues, and all this kind of stuff. Once we talking about CDC, we also check for convergence and divergence and reconvergence also of CDC passes, and we find all these cases. Combinational logic on CDC passes. We check for synchronizer structure, and so on. We have CDC viewer, which is convenient way to actually explore your design from clock perspective. Find your clocks and your clock domain clocks boundaries and see what design structures actually exist on each one of clock domain boundaries. You want to say that, for example, from clock domain A to clock domain B, for example, crossings to, crossings from, and then you find those crosses and see whether this crossing is synchronized properly or not. And this is another useful way to find information about your design with multiple clock domains. We provide different kind of graphical capabilities to debug CDC issues with cross-probing between schematic and CDC view. I will show you later on. You can highlight different clock domains in different colors in schematic to see better how they looks like. So in this case, you will see immediately which flop belongs to which one of clock domains. We have a concept of CDC schematic. Where you group your CD design view is partitioned across clock boundaries and corresponds to partitioning, say, strategy multi-clock designs. Basically, we group your design such that if there is one clock domain, then there is another clock domain, and you see your design structure, your synchronizer as a block. Basically, it's kind of separate, different design grouping of your design based on CDC. And definitely we provide debugging capabilities to click on your CDC issues, warning, and go immediately into your design. And here you can understand exactly how synchronizers are extracted what they include, and what is the issue. And this, for example, in the red line is CDC passes going from one clock domain to another clock domain. We also, if you don't have design constraints, we assist to develop the design constraints, and we provide automated way of doing that. And I will probably show you quickly an example. And finally, we generate constraints. As I already mentioned, constraints are generated in separate module, and that's why actually we want to make it portable. And this module, I'm talking about system Verilog assertions. This module can be instantiated as is in the test benches, and same level as a DUT. Let's say you design under test, and then you instantiate your CDC assertions in the test bench, and then you in simulation you can run them together. This CDC assertion module is only reads signals value, but without driving any other signal in your test bench. So it is really safe for test bench. You won't see any test bench functionality change after you add the CDC assertion, but you will add extra errors in a case CDC assertions are violated. I will probably go through example. This is basically examples of CDC assertions. You will see them in slides, and I will send you slides also. For different synchronizer types, which are different assertions. And now we can go to actual design example. Let's start show you design example in just a second. I will load it. Okay. Here I'm taking one of designs from the open course, which is Minimac. It is basically a Mac Ethernet Mac design. It's real design. It was used in many projects, and it's kind of it's stable in open course. So it's stable and verified, and also hardware tested and so on. But the question is whether it is sufficient to take this design and use it for the AUTO54. That's why we are running the AUTO54 verification of this project. And here I'm just, as you see, configured. I put on all the AUTO54 rules in project properties. And then now I'm just running verification and analysis. Here I'm running just regular linting. And here we have violations. Here we have violations grouped by chapters, and we can see what we can go through these violations and analyze each one of them. First of all, assignments. It finds duplicated signal assignments. Here is description of the rule. Okay, so in this we have a duplicated assignment of CSRDO signal, and here we have, as you can see, it's assigned in different places. You can multiple signal drivers. Here we can see that we have one in-out port, and the question is how we drive this port, how we control enable for this port. We provide recommended schematic on how to do that, and design violate the schematic. Then we can go to check for clocks and resets, proper clock and reset inferences. Here the rule requires that all registers should have a reset control. However, in our design, the question is which reset control. What you can do, you can click on this rule and then go to focus on policy editor, and then in policy editor you can see which reset types are allowed. So, for example, in this case, allowed types are asynchronous and none. So non-reset flops are allowed and asynchronous are allowed. And if what you can do, you can actually, in your design, you have also synchronous resets. And that's why you can do either two things. Either you had to wave, or you can configure your rule to have synchronous resets, and so on. So this way you can control reset types in your design. Declarations. All declared objects should be used in your description. unused parameter, unused port, and unused in other ports. So it's redundant stuff, which is it's a bad thing to do this in the AUTO54. So code should not be redundant in the AUTO54. Also, part of signals is not referenced. Hard-coded values.
Yeah. Alex, Asif here. So I just want to find out, how many more minutes because we can open up for Q&A.
Okay, I quickly I will go through 5 more minutes. Okay, and that's it. Okay, so thank you for reminding about time. I have lots of stuff to show you, and definitely I have maybe not enough time to show you all the features of Alint Pro here. Let's go to CDC verification of the same project, and here we actually switch to different flow from Lint Pro to CDC flow. And here in our policy manager, we'll configure only just put on and just click on CDC stuff, and then run verification phase by phase. Reset setup fails. Let's go quickly and second and clean it. Wave, and then continue just to be able to have some, as I mentioned, issues with with design. So here, for example, we extract CDCs, and here we have different viewers. We have viewers for clocks. The set viewer, you can view your clocks. You can see how they are. You can see them in schematic as well. You can bring them into schematic if you want to. Like just this filter in RTL schematic. You will see your clock trees. You will see your reset trees extracted out from design. And finally, you can go and see your CDC view. In CDC viewer, you can see your clock domains, clock domain crossings, which one to another, and how they are synchronized. And you can see some of them synchronized with byte FIFO, and some others may be synchronized with NDFF, basically 2 flip-flop, regular synchronizer, and so on. And you can definitely see each one of them in your schematic, and you can find issues. For example, if your synchronizer is not properly synchronized, so you will get an issue here in violation viewer. And finally, once you here we have 2 complex issues with convergence. We find complex passes, which are really important to we can just do a filter, and you will see that you will get complex two CDC passes which are converged in receiving clock domain, which is really a bad thing, and we have to analyze why it's happening. Maybe it's allowable, but we have to analyze our design. Once we do all this kind of work, we can actually wave. And once we wave it, basically you'll see that it goes from green to red, and then you're able to generate CDC assertions. Click on generate CDC assertions, and then CDC assertions are generated in your project folder under functional assertions SV, and then this is basically your system verilog code, and you can take this code and bring it into your verification environment, and just to accomplish a functional phase of CDC verification. Okay, so I will, because we don't have enough time, I will quickly go through other final topics of my presentation. We'll talk about tool assessment. Now, applicants are also responsible for tool assessment and qualification process for of any design verification tools used in the project. So, and basically, certification authorities may expect tool qualification data. And Alint Pro is also considered as a verification tool for your design. And to do that, Alint Pro, to help customers to pass through certification, Aldec provides the tool qualification data package for Dell A and B designs to help applicants. And deliverables include tool qualification plan, operational requirements, qualification testing suite. So for each check in the AUTO54 plugin, we have number of test cases, also passing and also failing, intentionally passing, intentionally failing. And basically we have all this regression in place. And when you can run this regression with all these tests, and generate reports in PDF and HTML format. This is an example of such report. With lots of checks, right? Here we have lots of checks, lots of tests, patterns, and wrong test failed, passed, fixed, and so on, right? And basically, we assist customers of running these checks. And finally, I will go to summary, and here will accomplish my presentation. Aldec provides the Auto54 rule set and CDC rule set based on industry experience and best practices. And both of them are essential for the Auto54 compliance. Alint Pro, basically, we talked about 2 plugins here, and finally, Aldec, as I mentioned, lately provides the required tool qualification data package for Dell A and or B designs. And here I will maybe finish my presentation, and we can go to Q&A session. Thank you very much.
Thank you, Alex. I will open up for questions. So we already have a few questions here. So how can I add a new policy? I mean, user wanted policy.
User wanted quality?
Policy, P-O-L.
Policy, sorry about this. Okay, so we don't allow customers to develop their own rules, right? Because it's a complicated process, and you have to go, and it's quite to integrate new rules in your design. So we don't allow customers to create new rules. What we do, we provide existing policies, and there is number of plugins. Basically, each one we call plugin. We have basic plugin, we have CDC plugin, we have premium plugin, which is actually complements basic, and we have plugin for System Verilog, and System Verilog is important to verify System Verilog constructs and so on. And we have plugins for RISC-V, actually, RISC-V designs, RMM for Synopsys, and also Stark. This Stark is very widely useful standard in Japan. And each we preconfigure rules, and what customers can do, they can actually enable, disable checks. As I said, also they can customers may change parameters of each rule, but if customers require more rules, so R&D, usually what we do, we implement new rules for customers. If customers require specific rules, so please provide us the requests of rule development, and R&D is going and developing the rules. That's how we enhance, how we actually implement our plugins, right? Does it answer the questions?
Yeah, I think so. Yeah. Anyway, thanks, Alex. I have another question here. I will just type it for you so that it's easy. You can see it in your chat box. Like, what's the difference between the double equal to and the triple equal to? So you can see it in your chat.
Okay, yes, I see it.
Yeah.
Double equal means, for example, if x equal y, so double this is an equation, right? So double equal, you cannot assign, you cannot check for x. For example, if one's left hand side and the right hand side are x's, so actually it will be you cannot check for x equal to x, for example, right? You can check some values other than x, undefined value, between each other. And triple equal also checks for x, proper x comparison. So for example, if you have x on the one side and other side, then it will also work. So in most cases, actually triple equal is checking for equations with possible x conditions.
I have another question here. With the DO254 plugin, can we verify clock and reset trees?
That's, yes, we do some checks for clock and reset trees in DO254 plugins, and I will show you. As you can see, there is part on clocks and resets, and I already mentioned about them. And this is the part where we verify gated clocks. We verify internal generated clocks and resets. We verify internal generated resets. And we verify proper clock and reset inferences. Okay, so we do have this subchapter of DO54 for verifying proper clock and reset trees. Okay. For example, you do not connect clocks to anything other than flip-flop clock pins. So if you connect clock as data to the data pin of your flop, you will immediately catch this issue, right? Sometimes you may want to do it, but it's actually a bad idea.
And there's another question here. Can ALINT verify block RAM timings?
First of all, there is ALINT Pro cannot verify timings at all. ALINT Pro is not it cannot calculate, it's not a static timing analysis tool. We don't propagate exact timing values and calculate values and calculate delays and so on. What we do, we propagate clock phases, like say clock A, and this we propagate clock phases to find clock domain crossings, clock domain regions, then boundaries, and then clock domain crossings. Okay, so we don't actually deal with exact timing in design. So, for example, if you add your design constraint file, and here is design constraint we added to Minimac. And here you specify create load period, let's say 40 to 10, and let's say some other values of 5 and so on. So for ALINT Pro, this values doesn't make any sense. Actually, it actually doesn't use this information. What ALINT Pro is using is information about phases of each input port. For example, here we see that this input port is synchronized with system clock, and other input clock synchronized with 5RX clock, and so on. This is important for ALINT Pro for CDC analysis, right? So we don't close timing. We do provide some hints on long combinational paths out from extracting it from schematics, from high-level netlist. But we are not able to actually to do real timing verification. Okay, so
yeah, there's another question. I think this is the last question for today because we are overshot already. How can I input block design like system generator model design in ALINT Pro?
I don't think you can put models into ALINT Pro, because ALINT Pro usually works more with RTL code. However, if your design also contains some behavioral blocks or some test bench block, we understand that this block is a behavioral or test bench, and we treat it differently. In general, what you can do, like say how you import. Here we have conversions, as I already mentioned. You can convert code from different FPGA projects right into ALINT Pro. You can, for example, do it from Vivado and Xilinx Vivado. Just click on XPR file on the project, next, and done. And we load project, we analyze it. If it contains different like IP, like out of context IP, so we put them in different projects. This is your main project, and we automatically load your library support for Xilinx, and we contain, as I mentioned, ALINT Pro contains all precompiled libraries for all tools. Here we can go to library window. Library viewer, and you can see that we precompile. We have libraries here for basically for Intel, Microsemi, Xilinx, and Simplify, basically for anything you want. And you don't need to do nothing with your FPGA projects. You can automatically port them here.
Okay, I think that's all we have from the questions perspective. So for further questions, what you can do is you can write an email to contact@prodigytechno.com, or you can directly write to Raghavendra or Nitin or Khalil. That is one thing which you can directly do that. The other thing I wanted to say was, since we had announced this Amazon gift voucher, right? So please, yeah, it is the last question. Yeah, so we want to announce that winner. So people who have been sitting patiently for 1 hour and attending the webinar. So let me just get the name here for the winner. Give me a minute. So yeah, so I get the name here. So the winner for today for the Amazon gift voucher is Arpit Patel from Physical Research Laboratory. So Arpit, our team will directly, marketing team will directly get in touch with you, and we will give you the Amazon gift voucher for 5,000 rupees, and right, and that will be given to you. Okay. And Alex, thanks for the wonderful presentation. And yeah, I think Alex is also showing the details, right? So yeah, you can also write if you have any specific questions. You can also write to Alex, or you can visit the Aldec website as well. So Alex, thanks for the wonderful presentation. I know it's very early morning for you there, and thanks for waking up very early in the morning and giving the presentation. I hope everybody enjoyed and learned a lot. So if you need further any of the individual webinars to be done in your company or in your organization, we would be more than happy to support you guys. You can contact Nitin, Khalil, or Raghavendra, any one of our team members. And with this, I'm going to wrap up the session. Thanks, Alex, and thanks everyone for the participation as well. Thank you.
Thank you very much.